So I've created a new file in Riza 3D, and what I want to do is import a three-dimensional DXF file. So we did this with a two-dimensional version. We can do the same thing with the three-dimensional version. One of the things I have to do is set up the vertical axis to match what I did in CAD. So with AutoCAD, oftentimes you have the X and Y being the plan, and then the Z is being extruded up. For some reason, Riza has the default being Y is the vertical axis, so we're going to change this to Z. That way our AutoCAD model will match the orientation of the Riza model. So I'll set that. Then I'll go here to import DXF. So this is the DXF file that I've created. Hit OK. CAD vertical axis is Z. OK. All right. All right, so that matches. This is exactly how I drew it in AutoCAD. This is, let's say, three arcs coming together, arches coming together. I'll actually create a pin here. It's similar to a three-hinged arch, except I'm doing it now with three pieces versus the typical three-hinged arch is a flat arch with a hinge there, a hinge here, and a hinge here. So we're doing it with adding this additional segment here, and then this is kind of bent off the axis here. So if I look at it from the top down, the XY, the typical three-hinge arch, this would be straight all the way across. So I've got two of them on this side versus the one. Go back to ISO. We need to define the members here that we have in the model. So I'll go here to spreadsheets and I'll go to section sets. I usually do this just to help me organize the model. And we'll just create one section set, and we'll use this for all of the arcs or arches in the model. So I'll create 24 inches deep, 12 inches wide. Call that A1 or Arc 1. Change that to 4,000 psi concrete. All right, and let's see, let's go to F2. We'll turn on the members here. Label. So now I'm labeling all the segments. One thing I'll mention, if you do have a curved section in your model, Riza doesn't like that, so you can't draw an arc in AutoCAD and then bring it into Riza. What you have to do is break up that arc into straight line segments. So I did have an arc in AutoCAD that I broke up into 1, 2, 3, 4, 5 pieces. So I did that for each one of my curves. So if you did have just a pure arch, again, you have to break it up in AutoCAD into straight line segments. Again, you can input all of these nodes in Riza. I just find it easier when you get to a little bit more complex models. It's easier to draw in AutoCAD and then bring it in as a DXF file. So let me go back to the members. Define the section set. So I don't want to use this default here that when I just brought in the DXF file. I'll edit it here and actually reassign all the properties here. So I want to do let's see, I can define it here. I can use the section sets, concrete, use my A1. If I want to define each one separately, I could do it here. Actually type it all in, but I find it easier just to define one first and then just assign it here. So now I've got my A1 for member 1. It's got that 4,000 psi concrete. If I wanted to, I could have created, an A1 and use that for all these, an A2 for those, and an A3 for those. I'm just going to use the A1 every place. In the AutoCAD, or in the demonstration version, you cannot copy and paste, so they restrict you, so you just have to type all these in. Okay. Let's just make sure I've got the orientation correct. So F2 brings up this dialog box. Hit the rendered, and that looks right. So I've got these oriented vertically, which is the way I want it. Hit F2 again. Let's just go back to the wireframe view. So now I've got that. Let's define the supports at the ends of the model. So this is my little pencil. That's the graphic editor. That's my support condition. Let's create a pin, and we'll put the pin at the ends of the arcs. Now all the other pieces are assumed to be fixed. So this connected to this, connected to this, every one of these joints is considered fixed, which is typically what we'd have in poured in place concrete. I will create a pin right at this location. Let's go back to spreadsheets, go back to members. We'll go to the advanced, and this is where I will release. I'll look at member 5, and depending on how you draw this, to be honest, I'm not sure which one's the IN and which one's the JN. We'll find out in a second. It depends on how you've entered these. Well, since I imported in AutoCAD, I don't recall, did I draw this one first or this one first? We'll go here, and I'm just going to guess that the end, this end is the J end. So I want to release this. Okay, so right now it's fully fixed. At the J end, I'm going to release the bending moments, but I'll keep the torsion fixed. Torsion fixed means that this can't spin versus this. All right, so we want to fix it across here, but in terms of, or sorry, we want to look this one here. We want to pin it across here, but we don't want this one to be able to spin or torsion about its axis. So this is the one I'm going to select here. It's just the bending moments that I want to release. Okay, and I was right. So that was the right joint to select. I'll do the same thing for member 10 and member 15. So 10, release this one, and then 15, let's see, I think it's that one. Oh, I messed up. So I released that side, so I need to switch that. Just hit the space bar. Actually, this one, I'm sorry. No, I did it twice, didn't I? I can type B as well, and that will bring it up. Okay, so now I've got the pin there. So 15, I'll type in B. I could go to the dialog box if I wanted to. Just type in B. That'll bring it up. Oh, wrong one again. Space bar, B. Okay, so I've got my pins here. So this is fully fixed. All these joints across here, all these joints are fixed, but I get to the end and I have a pin. Okay, and I've got a pin here, I've got a pin here, I've got a pin here. So again, if this were a flat arc or flat arch, it would be a 3-hinged arch. A hinge here or a pin here, hinge or pin here, and hinge or pin here. Okay, so let's define the loads, and I'll just look at a dead load on the structure. I'm not so interested in putting the different loads in and factoring them. I'm just more interested in the kind of the overall behavior of the model. So I'll just call this load case 1. For the dead load of the structure, I will put in -1. That'll account for all the concrete weight acting downward in the Z direction. And then I want to create a bunch of distributed loads. Okay, so I could go here and I could type these in, draw indicate the member, and then actually input the loads. But I'm going to do this graphically, so I'm going to get out of this. So inputting loads like a continuous load, putting in a point load or a joint load. This would be a point load, this would be a joint load. So the distributed load is here. So basic load case 1, I've only got one load case, so that's all I can use. It'll be in the Z direction, and let's just say that I've got 25 feet of tributary width on this one, and then I've got 12.5 here, and I've got 12.5 here. And let's say I've got 100 pounds per linear foot, or 100 pounds per square foot that's going to be applied to this, and I've got a 10-foot tributary width, so that'll give me 250 pounds per linear foot on this member. So again, just kind of guesstimate, what types of loads you're going to be placing, how much area do you have on this. And again, I'm just saying I've got a 10-foot tributary width on this one, and on this one, and I've got 100 pounds per 100 pounds per square foot. Excuse me. So let's see. So I'll say I've got negative 0.2, 200 pounds per linear foot, or 0.2 kips per foot. All right, and I will apply that to all of these. Okay. And for these, let's see, I will apply half of that load. So I'll assume that if I had 20 feet here, I'll put 10 feet on either side times the 100 pounds per linear foot. So I will use negative 0.1 and apply. So I will hit all of these. So these have exactly half what I had on the one arc. Okay. And I will put in the load combination. So I've only got one combination I'll consider. I'll just type in 1 here, load case 1, and I'll just put in a factor of 1. So we won't worry about factoring these. All right, let me solve this. Instabilities were detected. Okay, so this is often the first error that you will get in 3D. We usually don't get this in 2D. Again, it's because we've introduced this third axis and we get instabilities as a result. So it'll tell you, if you hit OK, yes, it'll tell you, it'll bring up a new model of where your instabilities are. So what often happens is you have too many pins in one location. Okay, so let me go into here, F2. Let me take off the loads for now. All right, so I have too many pins coming in one location. So what I'll do is I'll only pin the one side. So let's for the M5, let's take that off and say I've got a fixed condition here. Okay. Oh, still have instability, so now I have instability here. Okay. So one of the things that's happening on this model, this is pinned, and this is pinned. So what could happen is this arc could actually spin about its axis. There's nothing preventing this thing from rotating around the pin or rotating around the pin. So this thing could just be spinning. We don't have that in the two-dimensional version because it's flat and it's considered to be stable in and out of the page. Well, we don't have that in the three-dimensional version. So what I'm going to do is actually add an additional restraint where this can no longer spin about this point. It's still a pin in terms of bending moment, but it just can't spin about that point. Let's see. So I'll go to my support conditions, boundary conditions, and again, this is the problem with the three-dimensional version. That you've added that additional axis. You've created more potential for instabilities. So let's say I'm going to prevent rotation about the vertical y, or sorry, the vertical z direction. So I'll say that's a reaction. This is a reaction, and this is a reaction. So again, what it's doing is saying it cannot spin around the y-axis. All right, so let's now try to solve it again. And now we don't have any instabilities. So this model is now stable under that load. Okay, so let's look and see how it's behaving. I'm gonna get a different view here. And let's spin this around Z. Okay. Hit F2. Get my deflection. And animate. Okay, it's a little bit tough to see. Let's increase the magnitude here, or magnification factor. I'm going to go to rendered also. It's a little bit easier to read. Go to F2, deflection. Let's ramp this up to 100. So 100 times the actual deflection. So animate that. Okay. So what's happening, I have a lot of load being applied here, and this is actually pushing down, and it's actually pushing these two up, which is kind of interesting. Let's see, let's make sure I've got the loads in correctly. At 200. Let's see. Okay. So what's happening is so this is actually pushing down, and it's actually pushing these up. If I go into, oh, I'm sorry, it's the opposite way. We have more dead load on this side, so the overall load, total of 200 kips per foot, or 200 pounds per foot, or 0.2 kips per foot on this side, so 100 plus 100, and then a total of the same thing here, 0.2 kips per foot, or 200 pounds per linear foot. But I have more dead load on this side, right? Because I've got two arcs. So what's happening is these are actually pushing down and actually pushing this one up. So if I look at results, sorry, go to F2 again. We'll do this graphically. We'll go to members, and I'll go to the Z moment. So I have a positive moment here, and I'm actually getting a negative moment on that side. So if these were perfectly balanced, I would have the same moments on both sides, but again, because I have more dead load here, it's actually pushing this one up, and these are actually going down. I don't have any bending moments here at that pin, and this is what I'm getting here is kind of a classic moment diagram that you would get with a 3-hinged arch. That you get larger bending moments here in the middle of the arch, and then obviously there are 0 at the pin and 0 at the pin. Same thing on that side, 0 here, 0 here, with a maximum here in the middle. It's just a little odd here that's actually pushing up. You know, again, perfectly balanced, you would get the same moments on this side as you would get on this side, and they would both be the same, whether positive or negative. But here again, positive on this side, negative on this side. So this is something that I'd want to output in terms of the moment diagram. I can also look at the axial forces. Go to axial. They're almost uniform all the way through. They get a little bit bigger here at the bottom because there's more dead load. As I work my way down, more load is getting in the lower parts of the arc. So a little bit greater here, a little bit smaller here at the top. Let's see, what else can we do here? If I wanted to, I could look at the results for individual pieces. So let's say the M2 down here. I could get the axial load here. You can see again it's increasing here at the base, getting a little bit smaller here at the end. I can actually bring up the shears, and then I'm bringing up the bending moments here. And I could do that for all these various pieces. So this is something I want you to print out in terms of the axial loads, in terms of the moments, going back to the moment here, in this case the moment Z, and also get an animated deflection. Again, you can learn a lot about the model. I didn't expect this to be kind of pushing up like this, like it's doing, but makes sense, right? More dead load here, it's going to want to push this one up. These are going to want to go down. The other thing we could do is we could play around the support conditions. We could actually create springs here, which would kind of move out as this is undergoing load. These are perfectly fixed, so it's kind of a perfect world situation where you have a support, and that support is infinitely rigid, and this cannot move when it's undergoing load. Well, in structures we always have some type of movement, so we can oftentimes play around with this and actually assign a spring to make this thing kind of move out. Okay, so let's stop this, and I'll do another model where I actually play with the supports and do some spring conditions.